Hey, what's up, everybody? We're going to go ahead and jump into this and kind of talk about the nephron. Anytime you start learning about the kidneys, the craziest thing is that, like, if you read a typical chapter in a college textbook, you're reading all this stuff about the kidneys and you're reading about the urinary system, and you start talking about urine formation, and you start talking about blood pressure regulation, and you start talking about blood volume regulation, and all these hormones about angiotensin and enzymes like renin and hormones like EPO. And then you come to find out that the kidney is actually a really complex structure, but that inside the kidney, the only thing that's really responsible for all of that stuff is these little tiny microscopic tubes called nephrons. And then you come to realize that like 80% of the entire chapter is all happening inside these microscopic tubes called nephrons. So we're going to go ahead and jump into that. I want to kind of talk about the nephron a bit and really get down to the nitty gritty of what you need to know and what you need to understand when it comes to the nephron. Now, we're looking at an image here. This is not a nephron. Actually, what this image is a renal corpuscle. Some people call it a renal capsule. And if I back up for a moment and show you a picture or an image of a typical nephron, this is a picture of a typical nephron. This right here, okay, this is where glomerular filtration is going to take place. Some people have different names for this structure. Oftentimes it depends on who your teacher is and what textbook that they're using. For the sake of argument, I'm just going to call this whole entire thing the renal corpuscle. Sometimes you'll hear me say renal capsule or renal corpuscle. And this is where everything begins. Blood that comes into your kidneys comes in through this afferent arteriole and then passes into these capillaries called glomeruli. And then the blood comes out through the glomeruli. That's multiple. That's more than one glomerulus. This is one ball of like 50 capillaries. It's a glomerulus, but I'm having to talk about all of the nephrons at once. So blood comes into your nephrons via these afferent arterioles. They go into their glomeruli, and then the blood comes out through the efferent arterioles. Now, filtration is taking place right here. So what you have to understand is this. There's something in the blood that we want to pull out and throw away. The problem is that there's nothing in your body that's efficient enough to actually reach into your blood and pull things out piece by piece and then sort through it like that. The kidneys are your best shot at doing anything like this. So when we pull things out of the blood, what we wind up doing is we wind up pulling out most of what's in your blood. We pull out a lot of fluid and everything else that dissolves in that fluid. So that's what winds up being your filtrate. Your filtrate has a lot in common with your blood plasma, which, if you remember your blood plasma, 92% of blood plasma is nothing more than water. Blood plasma is the liquid portion of your blood. Red blood cells, white blood cells, and platelets, that's all the solid stuff in your blood. But blood plasma is the liquid portion. And in blood plasma, 92% of that is nothing more than H2O. So when you make filtrate, what you're doing is you're pulling out the water portion of plasma plus a lot of the different solutes that's dissolved in that plasma. So we see glucose, we see amino acids, we see sodium, we see calcium, we see chloride ions, we see enzymes, we see hormones. All that stuff gets pulled out at the glomerular capsule, or what some people call the Bowman's capsule, or the renal capsule, whichever name you want to use. They get pulled out at this point. Now, if we go forward a bit and we take a look at this image of this capsule, we can see where blood and all those structures are floating through. See, when we look at blood and you look at pictures of blood, you're watching True Blood, or you're watching some kind of movie or TV show and you see blood. All you see is this dark liquid stuff spraying all over the place. You see this dude get shot, this ninja chop. You see all these different things happen, and you see blood all over the place. And it's just this reddish liquid that we've all come to know and associate with action movies. But when you break down what's really in blood, there's all these things, all these constituents inside the blood. You got red blood cells, you got white blood cells, you got plasma proteins over here, you got solutes all over here. All this stuff is floating in your blood, and then it goes into the glomerulus. And what they did here is they take a section, a transverse section of that glomerulus, and then they blow it up right here in the circle so you can see the wall of the glomerulus, and you can see this is the blood that's flowing through the glomerulus, and then this is the outside of the glomerulus. This is the capsular space that we see out here. This same space in this circle on the right side of the circle is the same space you see in the capsule. And what's happening is things are passing through the small slits, these filtration slits. They're passing through the filtration slits, through the filtration membrane, and making their way into the glomerular space. So when you zoom in here, look at that. The red blood cells, they're too big to fit through the slit. White blood cells, too big to fit through the slit. Plasma proteins, look at that. They bounce right off. They're too big to fit through the slit. However, things like solutes, water, glucose, amino acids, ions, urea, hormones, vitamins, ketones, small amounts of protein, really, really small amounts of protein, very small proteins. They're all fitting out through these capillaries, and they're winding up out here in the capsular space. Amazing. Just absolutely amazing. So it's all out here. So all of this stuff gets out. Now you look at this list, okay? This list is what was originally in your blood floating around. We just took that out. You can't live without that stuff. You can't live without the water, the glucose, the amino acids, the ions, even a little urea is necessary in your blood. Hormones, vitamins, ketones, we can throw a lot of those ketones away. Small amounts of proteins, we probably want to use that. All this stuff, most of that stuff you want to keep, and most of that stuff your cells really want. So what's going to wind up happening is all of that stuff is going to make its way out of the glomerular capsule, out of the Bowman's capsule, out of this renal capsule, and into the tube, the rest of the nephron. And this first part is known as the proximal convoluted tubule. And so it's going to pass out. So, you know, how do things get across that slit? Well, one of the things you have to remember, and we don't really have time in this video to go into it because I really want to make this a crash. Oh my gosh, I got an exam in 3 days. What do I have to do to understand this stuff? One of the things that is responsible for making filtrate, which this is what we call the substance that comes out. We call it filtrate. That plasma that makes it out of the bloodstream, that makes it across this filtration membrane. We can't call it plasma anymore because it doesn't have all the things that plasma has in it. Because some of that stuff never made it across the wall because it was too big. So what you got is you got the water and everything that was small enough to fit across the filtration membrane. And due to that, we changed the name from plasma to filtrate. That's what this is. It filtered through the wall. How do you make filtrate? Well, that part is easy. But we need to go to another slide to show you how we're making that filtrate. Filtrate is actually produced this way. What winds up happening is we need something called glomerular hydrostatic pressure. Okay. Now, if you studied the capillaries in any other chapter in your anatomy and physiology class, then you learned something that was terrible. It was torturous. You probably hated it. Trust me, unless your teacher is kind of sadistic, they probably hated teaching about it too. And that is how things get in and out of capillaries. And if you don't remember, let me try to refresh your memory. Never forget this. When things come into a capillary, the reason why blood comes into a capillary is for one reason: exchange. We want to take things out of the blood and put them into the tissues. We want to take things out of the tissues and put them into the blood. That's the whole purpose of having a capillary. Capillary really has no other reason but to make a local place of exchange, because we can't get things in and out of arteries. We can't get things in and out of veins, but we can get things in and out of a capillary because the capillary is generally only one cell thick. And so it is hereby designed to get things in and out of it for the sake of the rest of the body. Well, glomerulus A glomerulus is a bundle of capillaries. So guess what? The game don't change, baby. We're trying to get things out of the glomerulus. And at the same time, some things are going to come back into the glomerulus. Why? That's the law of chemistry. Okay. And there's a lot of chemistry and physics in this. And we're going to just break it down to the bare necessities. When blood arrives at the glomerulus, you got to realize that this blood is arterial blood, which means that if it's arterial blood, it's moving with a higher pressure than venous blood. So this is blood. Let's retrace it back. The left side of the heart just contracted. It ejected blood out of the left ventricle into the aorta. All right. That blood travels down the aorta, down the descending aorta, through the thoracic aorta, down to the abdominal aorta, and straight into the renal artery. Guess where the renal artery is taking blood to? You guessed it, to the kidneys. So we just left the heart just mere seconds ago. That's a lot of pressure that's on this blood at this moment in time. And that blood is actually going to end up coming through the afferent arteriole and launching into the glomerulus, which means that it's under a pretty decent amount of pressure. Well, because of that pressure and because of these slits, pressure does not follow the lines. Okay. In other words, pressure is not driving around a curve and says, oh, look, the line curves to the left. I'm going to go with the left turn. That's not how pressure works. Pressure will escape anywhere from a confined area. All right. So like when you fill a balloon with air, you can thump the outside of that balloon and that air is in that balloon. Don't get too attached to that balloon, because the minute the pressure in that balloon finds an escape route, it will leave and that balloon will deflate. That's just the way pressure is. That's why pipes burst. That's why things blow up, because pressure is constantly looking for a place to escape. It never wants to be confined. And so you have blood pressure arriving at the glomerulus. And so guess what? Pressure wants to escape somewhere. And when it finds its place to escape, it finds it in the filtration slits of the filtration membrane that is made up of part of your glomerulus. So what winds up happening is the pressure forces its way through the filtration slits, out of the glomerulus, and into the capsular space. Well, guess what? Pressure in this case is going to push things along with it, which happens to be the fluid that's in your blood. So we're seeing a glomerular hydrostatic pressure, which is that blood pressure that's pushing things out, of a measure of 60, while osmotic pressure and capsular hydrostatic pressure are pushing things back into the glomerulus. You have to remember that osmotic pressure, or blood colloid osmotic pressure, is created because those plasma proteins that were still in the blood never came out. All right. And because of osmosis, osmosis will move water from a place of high concentration of water to a place of low concentration of water. Specifically, that reasoning being that water will move where the higher solute concentration is located. That's why a person can be out lost at sea and they can die from dehydration. It's a crazy thing when you think about it, that a person died being surrounded by billions of gallons of water. However, he or she was surrounded by billions of gallons of salt water. And what the water in his body thought was, oh, look at this high solute concentration outside of the body. If that high of a concentration of solutes are outside of the body, then that must mean that water must be in short supply out there. I'm going to leave the body and I'm going to go out there where the water, where the high solutes are. And that's how osmotic pressure occurs. When that water and everything leaves the capillaries, thanks to hydrostatic pressure, glomerular hydrostatic pressure, the proteins become more concentrated in the blood because you just took water out. It's kind of like having ice in a glass and you pour the water out of the glass. Well, the ice is still there. You probably didn't even notice how much ice you actually had in your cup until you poured all the drink out of your cup. Well, now that you poured the drink out of your cup, and now that the ice has become more concentrated and all in one space and still floating around, now you can see just how much ice you really got. And it actually poses an issue now. So In this case, you got all these plasma proteins. They're all floating around in the blood. That's still in the glomerulus, excuse me. Therefore, the solute concentration is higher in the blood rather than in the capsule. And so water thinks that it needs to leave. And so water then tries to go back into the glomerulus again. And then this capsular hydrostatic pressure is created because the water is moving due to osmosis. And anytime you have something moving like water, anytime you have water moving, it creates pressure because it's got movement. You have water moving, you got movement, now you got pressure. Plain and simple. Well, the amount of pressure forcing things out is higher than the combined forces of things pushing things in. And so we wind up having a net filtration pressure of 10, which is ultimately going to help push that filtrate into the proximal convoluted tubule. Speaking of which, if we move a little further along, let's see if I can find what I'm looking for. Sometimes it's important to control the GFR. If you've not watched any of the previous videos, you probably don't know what GFR is. GFR is glomerular filtration rate. And glomerular filtration rate, anytime you have the word rate in a name, rate is always referring to the amount of over time. Always remember that. I wish somebody had explained that to me when I was learning about rates and stuff. But hey, it is what it is. I'm telling you guys now. But rate is talking about an amount of something over time. So when you say glomerular filtration rate, glomerular because filtration is happening here in the glomerulus, and then filtration is the process that we use to force things across the filtration membrane and into the capsular space so that we can send it through the rest of the nephron. So GFR is going to always tell us just how much urine we're actually making. So in a case of stress or an emergency, the sympathetic division kicks in because stress in an emergency basically kicks in with fight or flight. And when fight or flight kicks in, we have sympathetic stimulation of the kidneys because the sympathetic nervous division is responsible for fight or flight, and he's going to contact everybody that he's interconnected with. At this moment, the granular cells of the juxtaglomerular apparatus, the JG, excuse me, darn. Boy, I'm 5 for 5, aren't I? Granular cells of the JG apparatus, they're going to release renin, which is an enzyme. And the enzyme comes into contact with angiotensin 1. The angiotensin 1 then is already coming in. Well, angiotensin 1 then comes into contact with ACE. And once it comes into contact with ACE, it then activates and becomes angiotensin 2. And then the angiotensin 2, what it does is it causes a contraction of these cells, which basically what winds up happening is it decreases the amount of blood flow that can get through here. And then, well, actually, to be specific, I'm sorry. To be more specific, it decreases the filtration surface area. So it causes all of these cells within the glomerulus to actually constrict. And so when you do that, you shrink the blood vessels, therefore shrinking the amount of surface area. And once you decrease the amount of surface area, you're going to ultimately decrease the amount of filtration that can take place because the surface area of a thing is its functional area. It's kind of like the difference between having 10 people help you wash a van and 2 people wash a van. 2 people can wash a van, but having 10 people wash a van is going to be a lot faster, a lot more fun, and a lot more, efficient. So this is what's happening here. Another thing that it'll do is it'll cause vasoconstriction of the afferent and efferent arterioles. And when you cause this vasoconstriction, you decrease the blood flow going into the glomerulus. Well, if blood flow decreases, then blood volume within the glomerulus decreases, which means that blood pressure in the glomerulus decreases, which means the GFR decreases, and then that decreases overall urine production. If we look at the opposite of that, if we say, oh, we want to increase GFR, okay, well, one of the quickest ways to increase GFR is just increase the blood volume or the blood pressure. That's simply the easiest thing to do. So let's say you wake up in the morning, all right? and you wake up. Oh, actually, let's say it this way, not waking up. Let's say you go to bed. When you go to bed, your blood pressure is going to ultimately go down. So when your blood pressure winds up, so what winds up happening is, look at the stimulus. You got an increase in blood volume or blood pressure. So blood volume goes up, okay, and blood pressure goes up. The atrial walls are going to stretch because of the increased pressure being placed upon them. Because remember, that blood pressure is coming from activity with the heart. The left ventricle contracts, it produces pressure, which goes out into the arterial pathways. And so the arterial walls stretch. And then the minute that occurs, that winds up stimulating cells in your heart to release ANP. Now, when ANP is released, look at the cascade of events that happens. To your left, we cause vasodilation of the afferent arterioles. When you do that, you increase the amount of blood flow going to the glomerulus, because the afferent arterioles open up, they get wider, more blood comes to the glomerulus. And then when you increase the amount of blood flow into the glomerulus, more blood volume is there, which means the blood pressure in that area is there, which means that the GFR is going to go up because we're producing more filtrate. On the right side of that, you see the angiotensin II production actually decrease, which therefore allows surface area of the glomerulus to increase. And the more surface area you got, the more filtration you've got. Therefore, you are increasing GFR, which is increasing filtrate concentrations in the nephron, which means that urine production goes up. So let's move on from that. I'm spending a lot of time here in the renal corpuscle, but once you get out of the renal corpuscle, everything's now flowing into the proximal convoluted tubule. When you look at the convoluted tubule image here, you're going to notice something real interesting. Let me show you this. This is the proximal convoluted tubule. You can see a piece here of the glomerulus. Here's the filtrate flowing in, and the filtrate flows into the tubes, and then they start calling it tubular fluid, because this is the filtrate flowing into this fluid. And here we are in the proximal convoluted tubule, and you notice that the tube is made up of cells. And look at what these cells are doing. The cells are offering paracellular transport, transcellular transport, and and you got transport proteins, and you got tubular secretions. What the heck is going on? Well, what's going on is this. We let a heck of a lot of stuff out through filtration. Do you remember that box? Do you remember what filtrate was? The fact that it was water and amino acids and glucose and ketones and urea and small proteins and all this random stuff, vitamins, all this random stuff coming out with the filtrate. Okay, you remember that. Well, all that stuff now enters into the proximal convoluted tubule. Now we got a problem. We have a huge problem, because we don't want to throw all that stuff away. If you do that, you're going to die within hours, because you're going to get rid of everything good in your body. So what we have to do is we have to reabsorb those substances, retake them, put them out of the tube and back into the blood where we first took them out of in the first place. So what we do is we do paracellular transport. This is movement of substances between epithelial cells. So there's a gap in between the epithelial cells, and some of these some of these constituents in the filtrate can squeeze in between the epithelial cells into the interstitial fluid right here, and then ultimately diffuse into the bloodstream and go back to the rest of the body. Some things will move through paracellular transport, and then some things are going to move through transcellular transport, which is the movement of substances across an epithelial cell. So para, which is talking about in between, trans, which means across. So paracellular is in between two cells. Transcellular is meaning across a cell. So they're using these special transport proteins to move things across the cell into the interstitial fluid and ultimately into the blood. You'll notice that these transport proteins all look different. You can see they all look different. The reason for that is because each one is responsible for binding a certain constituent out of the filtrate and allowing that substance to be returned back to the blood of the body. And see, each one of these is for a different thing. So basically, you got plasma proteins that will move glucose, and you got plasma proteins that will move certain amino acids. You know, that's just what they do. These things get reabsorbed, and this is where we see tubular reabsorption. These things move by this version or by this version or simply through diffusion, and they go into the interstitial fluid and into the blood. While meanwhile, we're able to take some things out of the blood that did not come out with the filtrate. Some of these things passing on by, some of these things in the blood may be able to be secreted from the blood into the tubule. So we move forward a bit more. Let's see, I don't want to lose my place. We're almost at the end of this one. I want to show you two more things. Actually, two things, three slides. The first thing I want to show you is the interstitial fluid concentration gradient that is created at the nephron loop. Some people call it the nephron loop. Some people call it the loop of Henle. The old traditional name is the loop of Henle. That's the way I learned it. New textbooks now are just calling it the nephron loop. And you can see here is the filtrate passing through the nephron loop. It's now going down the descending limb, and then it proceeds up the ascending limb. Outside, you have blood flow. You have a capillary that's flowing right along with the nephron loop. Notice that the blood is going in the opposite direction. This is countercurrent multiplication happening here. Okay, this is a countercurrent process. Countercurrent is when you got one thing flowing one direction, you got another thing going another direction, and both of them seem to contain something that has an effect on the other. Therefore, we get a special result by having both of them pass beside one another. So in this case, we've got water that's passing by, but at this point, water has salt in it. Now we got the blood that's passing by, and the blood has water and it has salt in it. So when the two of them dance and they go past one another, this is when, if this is very, very salty, guess what? Water is attracted to salt, so it will leave. If this is stimulated to allow salts to leave, then the salt will go into the blood and we'll see it come around and water will be picked up over here on this side. All right. Nephron loop and the vasa recta, which is a network of capillaries down there by the nephron loop. It's the site of countercurrent multiplication and countercurrent exchange. Notice what it does. It continues to reabsorb water and ions that begin in the proximal convoluted tubule. And so basically what it's doing is it's saying, okay, you know what? If we need more sodium, we can get it back over here at the nephron loop. And if we need more water, we can get it at the nephron loop. An example of what happens at the nephron loop is, let's say that your body doesn't, let's say your body is a little dehydrated and needs more water. Then what would happen is you would actually get rid of these salts. Actually, excuse me, I said your body is a little dehydrated, so you need water. So what your body would do is your nephrons would drop the salt off and allow the blood to pick up the salt. Well, once it picked up that salt, it would start pulling water out of the nephron, therefore increasing water concentration to your body. However, your urine in your nephron would become a lot more concentrated than it was before. And then the last slide is just talking about the distal convoluted tubule, the collecting tubule, and the collecting ducts. This is a site of extreme regulation. A lot of secretion can take place here at the DCT specifically, and the collecting tubule. Sodium can get reabsorbed. That can happen because of aldosterone and ANP. Remember, aldosterone leads to sodium reabsorption back into the blood. Wherever sodium goes, water follows. ANP wants to increase blood volume, which is ultimately going to, and deal with blood volume and deal with blood pressure and things like that. So if you reabsorb sodium, you're going to make water follow it into the bloodstream. Water reabsorption is regulated by aldosterone and ADH, because ADH is antidiuretic hormone. It reduces the amount of water you lose at the kidneys. So ADH will therefore tell the collecting tubule to reabsorb water from the urine. And that's great because you need that at times when you're dehydrated. And the water goes back into your bloodstream. And all of these different things that you're seeing here, notice that it's all about regulation. It's all about reabsorbing something to make something else happen. And I think that's probably the most difficult thing that people have with following the nephron, especially getting ready for tests and different things like that. It's really difficult for people to grab that concept, to grab that concept of the nephron, especially when you're talking about reabsorbing things. They just want to memorize one thing that happened and then go on about their business. Trust me, I understand. I was that guy. But one of the things you have to understand with the nephron is you're never just doing something just to do it. You're doing one thing to get a specific result. There's always the ulterior motive. If you watch TV shows, if you watch really good movies, if you watch spy thrillers, you know no one ever does one thing just for one thing. You're doing one thing to get another. And that's what makes watching all these spy shows and spy TV shows and all this stuff so interesting, because you do one thing, but everyone's curious to find out what that ulterior motive actually was. So yeah, aldosterone shows up at the nephron and tells the nephron to reabsorb sodium back into the bloodstream. Big deal. What was the real point of that? Well, the real point of it was the body knew that it was low on water. And so if we have reabsorbed salt from the nephron back to the bloodstream, water would follow, therefore increasing blood volume. And when blood volume goes up, blood pressure follows, and then everything can back to be happy. So that's all we got for that today. We'll talk to you later. Peace.